Topic isomorphism. The simple graphs G1 and G2 with vertices V1 E1 and vertices V2 and edges E2 are isomorphic. I mean, two graphs G1 and G2 are isomorphic if there exists a one-to-one correspondence are nothing but one-to-one and onto function f from V1 to V2 vertices of first graph to vertices of second graph with the property that A and B are adjacent in G. That means adjacency property should be preserved. If and only if f of A and f of B are adjacent in G2 for all A and B in V1, such a function f is called an isomorphism. So by this definition we can't understood, but by giving an example we can say easily what is isomorphism. But it is important to know that the isomorphism, two simple graphs are not isomorphic are called non-isomorphics. If G1 G2 are not isomorphic, they are called non-isomorphic. In other words, other definition for isomorphic, when two simple graphs are isomorphic, there is a one-to-one correspondence between vertices of the two graphs that preserves the adjacency property. Adjacency property means adjacency matrix of both graphs should be same. Isomorphism of simple graphs is an equivalence relation also we can call. Now observe, this is the example. Show that G and H are isomorphic. Now in G we are taking V comma E. V is vertices in G and E is edges in G. H equal to W comma F. W is the set of vertices in H and F is the set of edges in H. Now observe, if we are taking a function f like this with the mapping u1 is mapped with v1, u2 mapped with v4, u3 mapped with v3 and u4 mapped with v2 like this. F of u1 equal to v1, f of u2 equal to v4, f of u3 equal to v3, f of u4 equal to v2. Observe this mapping. Okay. Then if this f preserves a one-to-one correspondence and adjacency matrix, okay, if this is a one-to-one correspondence between v and w, one-to-one correspondence means this should be one-to-one and onto. Now observe how to check this is one-to-one and onto. Now check every pair in G, adjacent is there in H also with respect to F. So the adjacency property preserves if that satisfies. Now observe, for example, U1 U3. Observe here U1 U3. In G U1 U3 there is an edge. Observe U1 U3. Observe there is an edge U1 U3. Then what is f of u1, f of u3 is nothing but v1, v3. If u1, u3 have an edge, then there should be an edge between v1, v3 also. Observe v1, v3, there is an edge. Like this, not only these two pairs, we have to compare u1 with every other pairs, like u2 with every other edge, u3 with every other edge, and u4 with every other vertex. So like that we have to compare. Their images you have to compare. If we are comparing u1 u3 means their images are what, v1 v3 you have to compare. Now observe u2 u4, for example. u2 u4, is there any edge in G? u2 u4, yes, there is an edge between u2 u4. Then observe their images of u2 u4, v4 v2. Now there should be an edge v4 to v2, between v4 to v2 in H. Observe v4 v2, there is an edge. Like this, compare every pair. If at least one pair is not satisfying, then this is adjacency property is not satisfied. So you have to compare with here every pair of vertices. Now observe u2 u4 u3, for example. u2 u3, is there an edge? u2 u3, there is no edge. Now observe the images v4 v3, then there should not be an edge v4 between v4 v3. v4 v3, observe there is no edge directly. So like that you have to compare to the vertices of G and H. Of course, the edges of G and H you have to compare. So if every pair of vertices this adjacency property is satisfied, then we will say that F and G are, of course, sorry, F is an isomorphism between G and H graphs. Observe, there is a mapping given all these lines. Through F1 also, G and H are isomorphic means we can say mod V equal to mod W. That means number of vertices in G and number of vertices in H are equal. And of course, mod E equal to mod F. Number of edges in G and number of edges in H are equal. Of course, the degree sequence of G and H are same. Degree sequence means we will write the degrees of each vertex in a sequencing order, in an increasing manner. Okay, those sequences should be same. Degree sequence is nothing but we will write the each vertex degree in that graph in ascending order. Sequences should be same for both graphs. Then we will say G and H may be isomorphic but not sure. Okay, if F preserves the adjacency property, then we will say G and H are isomorphic. We will see these examples in the further videos clearly. Thank you.